So whatever this value is, unless it's extremely low, and it's 0, maybe we're not going to get up to where we need to be. But if it's some fraction of normal, the efficiency of the gas exchange process will bring it to equilibrium. Okay, great question. All right, so now we're going to adapt. I lost all my markers. 73, what was it? 48. Okay, so why are we going to adapt? What sets this off? How do we know there's a problem? Okay, arterial blood, PO2 is going to be low. We'll sense that with our carotid bodies. Okay, send signals on up to the brain, to the pons, where they'll oversee the DRG and VRG, right? Okay, what are we going to do? What adaptation happens here to bring us into a PO2 value of arterial blood that's safe? I heard increased ventilation, and you said alveolar ventilation rate. Yeah, either will suffice. Both are true. Right? We're going to increase our rate and depth of respiration. But what does that do? How does that correct the problem? I mean, we all acknowledge that, okay, we get more oxygen, but what's happening? Yeah.
Does alveolar PO2 more like that?
Perfect. The alveolar PO2 becomes more like the atmospheric PO2. Okay. Remember, we had a tidal volume of about 500 milliliters that goes in, right? And that's with a resting lung volume of about 2.5. Okay. So we're mixing air with air that's in the lungs. Okay. So if we increase our tidal volume or the frequency, we will increase the PO2 of alveolar air. So we can bring that much closer, and I like the way you said that. We're bringing it to look a lot more like atmospheric air. So we're moving the PO2 upwards towards 73. Now we'll never get to 73. Okay, so the most we could ever get is 73, let's say, but we can't. We can't ventilate our lungs that efficiently. But by altering the rate and depth of respiration, we move our alveolar ventilation rate upward, and that changes our PO2 of the alveoli. Okay, so if we get up to, I don't know, 60, that'd be great, right? That 60 in the lungs translates to 60 in the arterial blood. Okay. Any questions about how that works? Okay. Now, you've all heard of altitude sickness, right? Anybody have it? Not now, but if you have it now, you've got a problem. Although you're sitting pretty high in the back row. You've had it. What sort of symptoms do you have? Anybody? Yeah. Nausea. That's not good. What else? Anybody? Headaches sometimes. Yeah. So altitude sickness is it's worth learning about, not because we're all going to go to a high altitude, but I think it's a great example of a situation that people have to deal with, and we can sort of apply what we understand in order to understand the physiology. Okay? So we have increased alveolar ventilation rate, which we just described. Okay? No problem. It restores, or maybe restores, moves in the direction of restoring the PO2 of the alveoli and the arterial blood, right? Now, what is the effect, though, of increased alveolar ventilation rate on the pH of the blood? Okay, let me simplify. What effect does the increasing the alveolar ventilation rate have on the hydrogen ion concentration? It decreases, right? Can you tell us why?
Less
with hyperventilation, that is high degree of ventilation, we are releasing more CO2 to the atmosphere, right? So our blood CO2 levels go down. Less CO2 means less hydrogen, okay? So what does that mean for pH? It goes up, okay? All right. So our CO2 goes down, our hydrogen ion concentration goes down, pH goes up, okay? What type of alkalosis would we classify this as? Okay, respiratory. So I want to make sure that we're all on the same page. So respiratory alkalosis means that we have as a CO2-driven change in pH. Okay. And it's in the direction of making the blood more alkaline. Okay. A metabolic alkalosis would be the result of something other than CO2 changes. Okay. Maybe you're vomiting a lot, right? And you're losing hydrogen ions from your body. Yeah. Your blood becomes more alkaline. Okay, so this is respiratory alkalosis. Great. All right, so what happens here? When we have a low level of pCO2, how do the chemoreceptors respond to this? Or what is the response to the chemoreceptor stimulation? What would you expect if you had a low CO2 value? What would you expect to happen in your body? You're going to ventilate more, or you're going to ventilate less? Less. Okay, that's right. Because low CO2 is going to lead to less ventilation. Okay, so those chemoreceptors are going to be inhibited, right, by the CO2. And what happens is, because we're more sensitive to CO2 changes than oxygen, this sort of opposite response to the low oxygen pushes us back towards a normal ventilation. Okay? So if you follow me here, we start by having a problem of low oxygen, and we breathe more rapidly and more deeply. But that results in a low CO2, which causes our respiration to return towards a normal value. Okay, and this is the problem with altitude sickness. Okay, so we turn our ventilation back to pretty close to normal. Okay, and when we're back to this sort of normal breathing, we've got a problem, right? What's our problem if our breathing is normal in a low oxygen environment? Not getting enough oxygen, right? So this hypersensitivity we have to CO2 creates a problem of having not enough oxygen in the body. Okay? So there's some symptoms that accompany altitude sickness. I've listed 3 of them here. Keeping an eye on the time, but let's talk through these together in class. What do you know about a low oxygen environment that might explain pulmonary hypertension? Let's define that. What do we mean by pulmonary hypertension? The pulmonary vasculature has a high what? Blood pressure. Okay, so blood pressure in that pulmonary circuit we talked about is high. Okay, what might cause that? Soul. Have an idea? All right, what happens when we have pulmonary arterioles surrounded by a low oxygen environment? They constrict, right? Remember, this is that sort of counterintuitive thing we talked about, where the parts of the lung, or in this case it's the whole lung, that has low oxygen will constrict, diverting blood somewhere else, right? But if it's the whole lung, what happens? creating resistance, narrowing our vessels, what happens to the pressure? Pressure goes way up, right? Okay. So the pressure of all of the pulmonary circulation goes up because our blood vessels constrict in response to low oxygen. Okay. So what? We've got high blood pressure in our pulmonary circulation. Blood's still moving, right? We know, we've learned already in cardiovascular system that a high pressure leads to a high what? Flow. Great. So we're still moving blood, but at a higher pressure, right? So what's the problem with that high pressure? Any ideas? Yeah, it might lead to pulmonary edema, right? And how would pulmonary edema develop? Yeah.
Filtration.
We've got a high level of filtration of blood happening at the pulmonary capillaries, right? Can you unpack that a little bit? Why are we going to have more filtration?
Due to higher pressure.
Okay.
So,
High hydrostatic pressure of blood leads to more filtration, right? Okay, great. And where does that fluid accumulate? Yeah, in the interstitial fluids of the lung, including the alveoli. Okay. All right, so you can see how this low oxygen can lead to this pulmonary hypertension, right? Which of course is going to lead to this sort of exuding more fluid from the lung. These are all concepts we've had before, but you can see how this comes together, I hope. How do every other arterial in our body, they respond differently to low oxygen, don't they? What do? They dilate, right? Facilitating greater local flow of blood to those areas that may need it, right? So how does that work against you in your head, right? We've got low oxygen. We're going to dilate a bunch of blood vessels. Yeah.
There's nowhere for that fluid to go.
Yeah, there's nowhere for that fluid to go. So sending more blood to your head can be problematic, right? And this is what most often gives us headaches with altitude sickness. Fortunately, it's one of the first signs, okay? And then you could move down in altitude, or there are other ways of dealing with this as well. Okay. Any questions about how we got to these answers? It comes back to understanding the local controls that we've talked about in the past. We good? Okay. All right, if you're being quiet, there's no chaos, right? Okay, one last thing that sort of saves us from all of this problem, but it takes a while, is that our kidneys come to the rescue. Okay, so I told you kidneys are great. Kidneys will balance the pH in our body, and this takes a little while. Okay, but once we take care of the hydrogen ion problem, right? That we've got too few hydrogen ions present. Then we're going to take care of this suppression that the low CO2 is providing to the respiratory system. Okay. So initially, we're going to start ventilating more, right? Then we get low CO2 and we start ventilating less. Then we get all these problems, and then kidneys come to the rescue, fixing the pH problem, right? And then oxygen can properly stimulate the chemoreceptors, and we're fine. Okay. There's a long way to get there, isn't it? Okay, so when we cover kidneys, we'll talk about this all over again as a way to sort of incorporate that last part. Okay, but we've got to understand a little bit more about acids and bases before we get there. Okay, any last questions before we move on? Okay. All right, you knew it was coming. Okay, so what happens when we exercise, besides feeling terrible? Maybe it's just me. All right, so this is something we all know intuitively, I think, that when we exercise, or it doesn't have to be exercise, it could be any physical exertion, whether intentional or not, we start breathing more rapidly, right, and more deeply. Okay, so green line with going from a state of rest to exercise, maximal exercise, we're going to increase our ventilation. Okay, oxygen consumption goes up, right? Makes sense. Okay, so what's behind this? Well, at rest, we've got these values that we've learned about. And by the way, I was talking to somebody in office hours about this. Right, Sarah? Yeah. Please do yourself a favor and know these values, okay? I don't ask you to know a lot of values, but please commit those to your brain. To your memory. So at rest, the metabolism of our body cells consuming oxygen leaves us with a PO2 of 40 entering the lungs. And it comes up to about 100, 104. And yes, you can remember 100 if that's easier. As it passes through the lungs. Okay? CO2 goes from 46 after picking up CO2 from our cells, and it arrives having equilibrated after the pulmonary capillaries at 40. Okay? What's going to happen with exercise? What would you predict to happen to the PO2 in the venous blood returning from your body to the lungs? Would you expect it to be higher or lower than 40? Yeah, definitely lower, right? So as your cells are more metabolically active, they're going to be drawing more oxygen away from the interstitial fluids in the blood, right? And through electron transport, we're going to be soaking up that oxygen, right? Turning that oxygen into water. Good. I'm glad we got that figured out. Okay. What about CO2? Was 46, what's going to happen with exercise? It's going to go up. Okay? So that's not a surprise. What about on the arterial side? Once we pass this through the lungs, what's going to happen to the O2 value? Increase, somebody says. Somebody read and knows the correct answer is? I like to give you a hard time with that. What's going to happen? It's going to stay the same as before. Okay, so this is really counterintuitive. So what happens with the PO2 values is that it doesn't change a bit. Okay, you even with maximal exercise, you're not really changing the PO2 values in arterial blood. Okay, why? I kind of touched on this in the past. What do you think? Yeah. Yeah, the PO2 of that arterial blood depends very strongly on the alveolar air, not so much on the venous PCO2, PO2, excuse me. All right. So let me put that another way. The oxygen that comes out of the lung depends more on the air that's in the lungs than the blood that's coming into the lungs. Okay. So this is another example of how efficient the lungs are, right? We can raise CO2 levels, we can lower oxygen levels substantially, and it comes out the other side pretty much normal. Okay. So what does that mean for our chemoreceptors? What do our chemoreceptors see? Do they see lowered oxygen? No. But we're hyperventilating, aren't we? Why is this happening? I'm not asking you because nobody knows. We have a lot of things that we know contribute. Okay, so it's not entirely clear, but I want to point to a few things that should make sense to you. We have receptors in our muscles and our joints that inform our brain of movement, right? What do we call those things? Yeah, proprioceptors, great. Proprioceptors are sensory receptors that inform the brain of movements of our musculoskeletal system. Okay? So skeletal muscle joints tell the brain something. We also have a motor cortex, right? Remember your precentral gyrus issuing commands down to those skeletal muscles. It also sends information to the respiratory centers. Okay? So it seems that at least part of our hyperventilation is the result of our brain being aware that we're exercising, that we're physically moving. Okay? And it does not seem to be too heavily dependent at all on oxygen changes in the arteries, because there doesn't appear to be much, if any. Okay? There's some idea that they're conditioned responses, right? So you start running and your body learns from this, so that, in anticipation of all of that proprioceptive input and so on, we can have a conditioned response, of course. Okay? That can't be all of it. And then there's a theory that there are some oscillatory changes. Okay? So what this means is you've got blood constantly flowing through your lungs, right? When you inhale, what happens to the PO2 value of your lungs? When you inhale, what happens to the PO2 of your alveolar air? It goes up, okay? And then as you're exhaling, and before you inhale again, what's happening to that PO2 value? It's declining a little bit, okay? So there's some thought that the arterial blood reflects those changes as well. That beyond our ability to measure, okay, there's a lot of hand waving here. There are slight differences in the arterial blood over time, okay? So that if you were to lay out the blood in a column, you'd see there's some pieces of it that are really high and some that are low in between. It's a hypothesis. All this to say, we don't have all the information to fully account for what we see and all observe, which is when we exercise, ventilation goes up. We just can't fully account for it. Okay. The last topic I want to talk about, and if you want to read about that, I did not assign this as part of the reading, but because it's relatively short, if you want to read it, there is a section in your book, and you can look for that, okay? Hypoxia is a really important thing to understand, and many of you I know are bound for clinical professions, so you should be aware of this. Hypoxia, in very generic terms, just means that we have deficiency of tissue oxygen, okay? Not enough oxygen in our tissues. And the causes for this could be a variety of things, and these are all things that we've kind of talked about in different pieces, but I want to put them here together. So the worst of these, the worst name for these is hypoxic hypoxia. This doesn't tell you a whole lot, does it? But what this means is that this is your arterial PO2 values are low, okay? And why might this occur? What's an example of something that would give you hypoxic hypoxia? Huh? Altitude, right? You're at a high altitude. Yeah. What's a lung disease we've talked about that might impair the ability to get oxygen to the lungs? Emphysema, right? Another type of hypoxia is anemic hypoxia. And this has to do with maybe you have a normal PO2 value, but you have low oxygen content. Okay? So maybe your hemoglobin is insufficient in its concentration in the blood. Okay? There's ischemic hypoxia, where this would be a local hypoxia, right? You think of an example we've seen before where we have ischemia of some variety. Yeah, heart attack, myocardial infarction, right? We have a coronary artery that becomes blocked. inadequate perfusion, right? And so that tissue becomes low, but it's not because of a problem with the lungs, not because of a problem with your oxygen carrying capacity, but now it's delivery of oxygen in the blood locally. Okay, so it's a vascular problem. And then the last of these is histotoxic hypoxia, okay, where the cells that are ultimately using this oxygen in electron transport are not able to adequately use oxygen. Okay, example of this is cyanide poisoning, and we'll talk a little bit more about this topic real briefly when we get to metabolism. Okay, so we'll talk about that. But you can see there's lots of different ways this could occur, right? Okay, so if you have any of these 4 types of hypoxia, I'll tell you that some of them are not going to be accompanied by chemoreceptive, being stimulated, and ventilatory changes. Okay. Which of these would be accompanied by some sort of compensatory change in ventilation? Hypoxic hypoxia. Why? Absolutely. Arterial PO2 changes, and that's what we sense. What about the rest of them? What if we have anemia? Remember our 50% hemoglobin example? Can we sense that? Not here, no. Our kidneys can actually respond. It's the kidneys again. The kidneys can actually respond to this with production of a hormone that stimulates red blood cell production. We'll talk about that later as well. All right, but yes, the rest of these cannot be sensed by the carotid bodies. Okay. So in terms of how the body is going to respond to these, we have cellular responses to lack of oxygen that shift our metabolism. But we're usually, if this happens in humans, we're going to have some necrosis and probably death. Ischemic hypoxia, how can we respond to that? Local vasodilation, absolutely. Local vasodilation will happen to those arterioles in response to low oxygen. Perfect. And maybe that fixes the problem, maybe it doesn't. All right, so we have anemic hypoxia, and the response here is carried out by the production of a hormone. Let me make sure we're all on the same page. It's called EPO, which stands for, anybody? Yeah, erythropoietin. Stretching my spelling limitations. Okay, EPO. And this comes from the kidneys in response to inadequate oxygen content. Okay. And we said we've got local vasodilation. Okay. And we don't have a really good response here that's going to save us from histotoxic hypoxia. Okay. We can't have some metabolic shifts in fuel partitioning and things like that, but we'll save that for another time. Okay. So really, in what we've talked about today, and changes to the arterial gases, it's really only the hypoxia that's going to elicit a response from the body. Okay. Last thing, we got, what do we have, 4 minutes? Perfect. All right, so long ago, you had different anatomy. Okay? You've all learned about this, I think, in Biology 252, that there is a structure called a fossa ovalis between the two atria. Fossa. Oops. That reflects a foramen ovale in fetal life. Okay? And what this is it's a shunt that allows blood to flow from the right side to the left. Okay? Now, after you are born, this to have a null of you. After you're born, what happens is a little flap closes. Okay? And it has to do with pressure changes that, come see me in office hours, we'll talk about this. It's cool stuff. But what can happen in a small percentage of the population is that it doesn't adequately close, or doesn't fully close. And this is called a patent foramen ovale, patent meaning open, or patent if you prefer. And even adults have this. A study on cadavers shows something like 10% of all of us have this, although it's not functionally a problem. Okay. So if we have a shunt that allows blood to go from the deoxygenated right side over to the oxygenated left side, you can see where we might have a problem, right? We can turn blue as a result of inadequate oxygen. Okay. What type of hypoxia would this be? Who had the most votes here? Hypoxia. Somebody give me a pitch for this. Tell me why this is a good idea. Why hypoxia? What's happening? If I tell you it's right, will you raise your hand? Yeah, go for it.
Venous and arterial blood, both like deoxygenated and oxygenated blood are like mixing.
Yeah.
So it's as oxygenated as it.
Okay, let me repeat that. She said mixing venous blood and oxygenated or arterial blood results in a PO2 that's going to be somewhere between 100 and 40, right? So it's going to be, we're going to have a low arterial blood PO2, right? Okay, that's the correct answer.